Hello, my name is David Smith, and I will be talking about X-ray lithography. In this presentation, I will be going over lithography in general and the motivation behind X-ray lithography and some key optical concepts behind X-ray systems, and as well as main variables that an engineer would design around. And lastly, I will talk about some practical challenges and applications at the end. So by the end of the presentation, you should have a rough understanding of why X-ray lithography is so prominent in research currently, and what are the applications, what are the uses. So firstly, what is lithography? Well, lithography is a pattern transfer process used in microfabrication, primarily in semiconductor fabrication or in the creation of MEMS devices. As you can see in the image here, we have a photolithography process, which involves a wafer, a substrate, and a photoresist, which is coated on top of it, and a mask aligned with the wafer and photoresist combination. And in this case, we have likely ultraviolet light that is etching out the substrate using the mask pattern. So with this pattern, very small features can be created on the orders of nanometers. The main motivation is going to be feature sizes. In the semiconductor industry, the current pressure point is how many transistors you can fit onto your chips. So the smaller features, the more money you'll be able to make, and that is why these technologies are pushing towards smaller and smaller features, and X-ray lithography is currently the answer to pushing past extreme ultraviolet technologies. As you can see in this image, we have an X-ray source through guide mirrors and a mask onto a wafer. So it is a similar concept to the ultraviolet photolithography image from the last slide, but there are some different technologies associated with the smaller wavelengths and the deeper penetration. Now I will discuss optical concepts associated with X-ray technology. The biggest one here is going to be refractive lenses are not going to work in the same way that they would for photolithography technology. And that is because X-rays have an index of refraction very close to 1 and often less than 1. As you can see in part A, we have visible light passing through the refractive lens and refracting towards the normal. But the opposite is true in part B, where the X-ray ray passes through the refractive lens and refracts away from the normal. So a refractive index less than 1. And in part C, we have the case of total external refraction, where the ray completely bounces off. So as you can see in this figure, there is a need for different technologies in order to create a focusing effect. And that's where grazing incidence and multi-layer Bragg mirrors are used. A grazing incidence mirror will use the concept shown in part C, where the X-rays hit a surface at a very shallow angle and undergo total external reflection, while the multi-layer Bragg mirrors are a stack of thin films to reflect specific X-ray wavelengths. Additionally, zone plates could be used, which I will get into later, but the main idea here is to replicate the concepts in lithography, and that is focusing light rays or electromagnetic rays. So replacing the refractive lenses with this science allows to keep the same workflow in the same system as shown before, without having to completely redo the idea of lithography. Secondly, as far as optical concepts are concerned, diffraction is again important. It is going to limit your resolution, and that is because the smallest feature you can resolve is on the order of wavelength. It's proportional to the order of wavelength and numerical aperture. So again, smaller features, smaller wavelengths, common concept here. Next, I will discuss relevant variables to someone who might be in industry, such as a process engineer, working on their X-ray lithography system. So, of course, wavelength range is something that can be tuned and tweaked. The typical range is going to be in the few nanometers, but smaller wavelengths theoretically will give better features, but they require more specialized sources and much stricter constraints on tolerances and control systems and material quality and efficiency. So this is something to consider. Secondly, optical element choice is another idea here, where we have at the very top we have a zone plate that is focusing the beam, and second we have a grazing incidence mirror at the very top, and the circular image is going to be the zone plate, and the bottommost image is going to be the Bragg reflector. So choosing which is most appropriate is also something that needs consideration due to the constraints involved. Lastly, I will discuss applications and practical challenges. This image at the top is a MEMS device. X-ray lithography is useful in this area if you need high aspect ratios, tall, thin structures. X-ray lithography is also good for nanophotonic and micro-optics fabrication. And some challenges, like I discussed earlier, will be optical misalignment and, of course, overexposure, which can damage your substrate. Here are my references.